So in chapter 10, we're going to start looking at gases and gas laws. So let's do some defining here, or look at some of the properties of gases. So first, gases expand to fill the container. So they will expand and take up the whole volume of a container. They can expand, which we saw from the, that's P, which we saw from above, expand, and they are compressible, which, unlike solids and liquids, means their volume can change. For a solid and a liquid, their volume is relatively constant. It doesn't change much. So another thing, gases will mix to form homogeneous mixtures. Okay, so we're going to see in chapter 11 that that's not really true with solids and liquids. And we also saw in chapter 4 how we could try to dissolve some solids into liquid, and it doesn't really work that way. Some things, like some solids, are insoluble, so they don't dissolve. And that's not really true for gases. Gases will mix to form a homogeneous mixture. So if we had a sample of gas, and in it we put, say, oxygen and helium, we would expect them to be nice and equally distributed. So there's no clumping or anything like that, so they form homogeneous mixtures there. Okay, so before we can really get in with gases, we describe what's happening with a gas based off of its temperature, its volume, the number of particles that are there, and the pressure. So we haven't really talked about pressure yet, so let's kind of start in with that. Okay, so I'm going to go back up. Let's go down here for now. So pressure is defined as a force over an area, or F over A. Okay, so a force over an area. So you can think of a force as like a push or a pull, and then area is, area. So you can think of a pressure of a gas as collision of gas particles with the container they're in or with each other. So force comes from collisions. Okay, so let's kind of go back up here, pressure. Okay, so we had force over area equals pressure. And my sort of terrible drawing here, so if I had a balloon, that comes from collisions. So I'll draw a little arrow here, collisions. Okay, so units. So there's derived units here. So the SI unit for force is a Newton, and then area is meters squared. So newtons per meter squared, and sort of our shorthand unit for that is a Pascal, P-A-S-C-A-L. Okay, so that's our derived SI unit, but we are going to see, when we come back up here, we're going to use different units for that. Okay, so to measure pressure, we use something called a barometer. So this is sort of this terrible drawing I have here. So barometer. So the way a barometer works is you have some sort of liquid, and mercury is often used because it's so dense. Okay, so we have a liquid, so this is mercury, and this is exposed, this reservoir of mercury, to the atmosphere, and then you have a tube where up here is under vacuum. And so vacuum there. So what happens is that if you apply pressure to the reservoir of mercury, you can get mercury to travel up into the tube. Okay, so if pressure is applied, say from the atmosphere, then the mercury will rise up into the tube, like this. And the distance that it travels up the tube is proportional to the pressure. So this height, how far it rises in the tube, H is the pressure. So one of our first pressure units are called millimeters of mercury. So millimeters of mercury is our next one after pascals, and that is how far, again, this, that's Pilgrim, he says hi. So that millimeters of mercury is, again, how far that mercury travels up into that tube. Okay, so for millimeters of mercury, we have 760 millimeters of mercury is equal to, let's see, our pascals here, 1.01325 times 10 to the 5th pascals. Okay, so that's our equivalent pressure for millimeters of mercury and pascals. Okay, so how, again, how does this work with this height? So if we look at a column of mercury, it has an area, and again, we're measuring the height. So if we go back to our pressure equals force over area, we can express the force as the weight times gravity. So on Earth, weight is the same as mass, because the weight and the mass on Earth are the same. So weight is mass coupled with the force of gravity. So again, because we are on Earth, we define mass and weight to be the same on Earth. But your weight would be different, say, on the moon or on the sun or something like that, because gravity is different there. Okay, so force equals weight times gravity, or equals mass times the gravitational constant G. Okay, so we can also express the weight or the mass of a particular substance as its volume times its density. So since we're looking at a column of mercury here, it would be nice to express it in terms of its volume, say, instead of its mass. So we can have volume times density is equal to the mass. And also volume, since we do have this factor of area in pressure, we can express the volume as an area times a height. So our area here, our sort of pi r squared here, and then our height here. So the area times the height would give us our volume, so area times height. Okay, so if we go back to pressure equals force over area, I can take my sort of mass times gravity and substitute that in. So pressure equals mass times gravity over area. So this would be of my, for example, my mercury in this tube. Okay, so I'm deriving, again, an expression for this. So my mass of mercury in this tube times the gravitational constant divided by the area. Okay, so more substitution. For mass, I can substitute volume times density. So we get volume times density times gravity over area. Maybe you can see where this is going. Area, volume equals area times height. So up here with volume, I can substitute in area times height with still my density and my gravitational constant divided by area. So then my area will cancel, and I get an expression where the pressure in, say, a column is equal to the density of the liquid times the gravitational constant times the height. Okay, so if you take all of this into account for mercury at sea level, so at regular sea level, sort of, regular conditions, the pressure is such that the height of this column of mercury would be 760 millimeters. Okay, so that's how a barometer works. So you can make a barometer out of a lot of different things. So there is a question in the textbook that says, hey, what if your barometer was made of something like water, or if it was made of ethanol? All of this still stands true. The only difference is you're going to have different heights because your density of your material in your barometer is different. So if it was, say, alcohol or water in here, you would need to use the density of alcohol or water. And you'll have to see what height of that particular material would give you that same pressure. Okay, so that's how a barometer works. So a couple other units of pressure before we move on. So we have millimeters of mercury. We have the SI unit of pascals. So we also have atmospheres. So 1.00 atmosphere is equal to 760 millimeters of mercury. Okay, so atmosphere, 1.00 atmosphere, that is defined as the pressure at sea level. So the column of air pressing down on the top of your head is equal to 760 millimeters of mercury, or 1 atmosphere. We also have 760 torr equals 1 atmosphere. So torr, that's a unit of pressure named for the gentleman who came up with this barometer. So he gets a unit named after him, the torr. Torr is the same as a millimeter mercury, which again, he is the inventor of this barometer. Let's see, any other good ones? Oh, and bars. So we have 1.01325 bar equals 1 atmosphere. So those are almost identical. Bars and atmospheres, they're almost interchangeable. Okay, so I think we got them. We have the pascals, which sometimes are represented, excuse me. All right, sorry about that. The dogs got all crazy. So we have the pascals that sometimes are written as kilopascals. So you'd have 101.325 kilopascals. And again, our millimeters of mercury and things like that. Sometimes you'll run into some, again, these are more used in science in the USA. Since we are still clinging to those sort of outdated units, you might see PSI, which is pounds per square inch. So you'll find a conversion factor for that in your textbook somewhere. Also, we see inches of mercury. So you can find, that one's not so bad. You just have to convert inches to millimeters and you'll get inches of mercury in terms of millimeters of mercury there. So just a standard, say, distance conversion of inches to millimeters will get you that conversion there. So these ones, again, really only seen in the USA because they have those imperial units of inches and pounds and more inches. Okay, so let's take a look at sort of how pressure is measured. So a lot of times we use what's called a U-tube. This one's kind of more square in shape, but if you have the end open to different things, changes in the heights of your two sides will give you something, will let you be able to measure pressure in relation, say, to the atmosphere. So in this one, we have both ends open to the atmosphere. So you get atmospheric pressure pushing down on both sides. So we have the two sides of this equal in height. So height of A, so say from corner to top here, the height of A equals the height of B. Pressure of A equals the pressure of B, which is atmospheric pressure. Okay, so what happens if, say, we were to close off one end and put a reference gas inside? So on this side, we have some gas, and over here we have the atmosphere, still open to the atmosphere, pressing down. Okay, so now the heights of the mercury inside are different. We have A up here, and we have C down here. Okay, so if this has pushed this level, again, remember they used to be equal. If this has pushed this all the way down, it's safe to say that the pressure over here on this side is greater than atmospheric pressure. So the pressure of our gas is greater than atmospheric pressure. So pressure of gas greater than pressure of the atmosphere there. And again, we know that because now this level is lower. The only way to lower that down, again, remember forces are pushes. So the force of this gas is greater than the force of the atmosphere, so it's pushing it down. Okay, so if we draw a level over here and call this B, the pressure of the gas here at C, A, the atmospheric pressure, but this line here, pressure B, is the same as the pressure of our gas because, again, equal pressures, if we go back up here, equal pressures have equal heights. Okay, so pressure of C is the same as pressure of B. And the pressure up here is much less than the pressure here, because this point here at B has this whole weight of all of this mercury sort of acting upon it. So the pressure here at B is greater than the pressure here at A. At A, you just have the atmosphere acting on it, but you can see at B, not only do we have the atmosphere acting on it, but we have this column of mercury from point A to point B. So we can say the pressure at point C is equal to the pressure at A, which is the atmospheric pressure, and also this added pressure we get here of this column of mercury. So if we found the pressure of that height, that H, that would give us the pressure of this portion right here. So the pressure of C would be equal to the atmosphere plus that pressure due to that added height there. So the atmospheric pressure, again, plus the pressure exerted from this here by saying that this point is equal to this one. So what if we would have had drawn a third one? So I'll kind of do a rough sketch. So what if we had, again, our nice sort of U shape here. Okay, so this one, well, I didn't mean this to be there. I want this one to be open for the atmosphere. So the atmosphere is still acting down. We still have our point A. Now let's say that we have our gas inside. Now let's say our point C is right here. Okay, what could we say about this one? So if we draw a point over, we would have, we could call this one B. So we have now over here, this height is higher than this one. So now we know the pressure of the gas is less than the pressure of the atmosphere. Okay, so the atmospheric was able to push it up even higher on this side. Okay, so pressure of gas is less than the pressure of atmosphere. So we still have this height right here. So we wouldn't want to add the atmospheric pressure plus this. So for this one, we would have pressure of A, which is the atmosphere. And if we take that and subtract, here's our height, the pressure of that height, we would equal the pressure of the gas. Okay, so in this case, because we've moved the column up over into the gas side, the atmosphere has a stronger push than our gas does on this side. So we would expect it to be less, and the height that it moves is how much less than the atmospheric pressure. So here it pushed it down a little bit more, so it was a little bit more. So we added the pressure of the gas to the atmospheric pressure, or the pressure of that height. Here we would want to subtract because we do know the atmospheric pressure is more. Okay, so that's how pressure is measured. Okay, so now we're going to look at some gas laws. All right, so gas laws. We're going to start at the top. So we'll do the first half and then we'll go down. So early scientists started experimenting with gases, and that's kind of how a lot of our stoichiometry came to be, and a lot of our theories on how matter is put together all come from the experiments that were done working with gases. Okay, so the first one we're going to look at is called Boyle's law. So what Boyle's law, or Boyle's experiment did, is he kept temperature and number of gas particles constant. And what he did is he wanted to measure volume and pressure changes. So he would say, get a sample of gas, enclose it, have a particular volume, measure the pressure. Then he would change the volume, measure the new pressure, change the volume, measure the new pressure, so on and so forth, without changing the temperature or changing how many particles are in there. So these stay constant. And what he found is that if he plots volume and 1 over pressure, he gets a straight line, which means volume is proportional to 1 over pressure. Okay, so we call these inversely proportional, which means if volume increases, then our pressure decreases. And if our pressure, say, increases, that means the volume is going to decrease. So they have the opposite effect if you do one of them. So inversely proportional, and we have Boyle's law given as P1V1 equals P2V2. Okay, so if you have the pressure and volume at one set of conditions, and say you change the pressure to another set of conditions, so long as the temperature and moles didn't change, you can calculate the new volume with this simple relationship right here. Okay, so the next one is Charles' law. So Charles' law is keeping pressure and number of moles of gas constant and looking at volume and temperature changes. So what Charles' law finds is that volume and temperature are directly proportional. So this means as volume increases, temperature also increases. So here, that's T. So as volume increases, temperature also increases. Or if you decrease the volume, eventually you get to a place of 0 temperature, 0 Kelvin, or negative 273 degrees Celsius. So the point at which this sort of crosses the axis here is our absolute 0. So this is no kinetic energy essentially of the sample here. Okay, so volume is proportional to the absolute temperature. So what we mean by absolute temperature is this is measured in Kelvin. Okay, so whenever we're doing gas laws, our temperature is Kelvin. We can measure it in Celsius, but when we want to do any sort of calculations, we have to make sure that is in Kelvin. Okay, so we have 2 more. Going down here now to our second set of gas laws. So our next one, we're going to look at Gay-Lussac's law. So for Gay-Lussac's law, volume and number of moles are held constant. So we're looking at pressure and temperature changes. So what Gay-Lussac found here is that as you increase the temperature of a gas, the pressure increases proportionally. So P is proportional to the absolute temperature. So they're directly proportional. Okay, so that's Gay-Lussac's law, and again, absolute temperature. So if we put that together, we get P1 over T1 equals P2 over T2. I think I forgot Charles' law. So Charles' law, V1 over T1 equals V2 over T2. So again, these are 2 conditions set. So you have an initial volume and temperature, and say you change the temperature of the gas, you can calculate the new volume. So same here. If you have an initial set of pressure and temperature, if you change the pressure of the gas, you can calculate what the new temperature would be. Okay, so 2 sets of conditions here. All right, finally we have Avogadro's law. So Avogadro's law, we're holding pressure and temperature constant, and we're looking at changes in volume with the number of moles of gas. So Avogadro finds as you increase the number of moles of gas, the volume increases proportionally. So volume is proportional to moles of gas. Okay, so if we put that together, we get V1 over N1 equals V2 over N2. Or same thing, if we have the volume and number of moles of the gas, if we add more moles, we can calculate what the new volume should be, so long as pressure and temperature are remaining constant. Okay, so what's very important also about Avogadro's law is that we can use that to compare different gases. Okay, so I'm going to flip this over. For example, kind of going, staying with Avogadro's law. For example, let's say we had 2 H2 gas plus O2 gas to give us 2 H2O gas. Okay, so we have this reaction here. So let's say the pressure is normal 1 atmospheres and that the temperature is, regular room temperatures of say 298 Kelvin. So let's say this doesn't change. Okay, so we have pressure and temperature constants, so an Avogadro's type of situation. So what this allows us to do is essentially interchange volume and number of moles. So for example, let's say we had one, we'll say we have 1 liter of H2 gas. How many liters of O2 gas are needed to react? Okay, so if pressure and temperature are remaining constant, which they are in this problem, I can essentially interchange volumes and moles. Okay, so I can say instead of 2 moles of hydrogen react with 1 mole of oxygen, I can say 2 volumes of hydrogen react with 1 volume of oxygen. And this is essentially how stoichiometry started. It was with gases, because they could see that gases combined in these volume proportions when you kept pressure and temperature constant. So what this allows us to do is 1 liter of H2. And again, we know that we can interchange moles. So instead of a mole ratio, I'm going to build a volume ratio. So I can say that there's 1 liter of O2 that reacts for every 2 liters of H2. Okay, so I built a mole ratio, but then I turned it into a volume ratio here. And I can do that because, like I said, the pressure and the temperature are constant throughout this whole process. So I would need 1/2 of a liter of O2 gas. Okay, so you're able to use this as sort of a shortcut in doing reaction stoichiometry, because if the pressure and temperature are remaining constant, and again, I picked 2 random pressures and temperatures, it doesn't really matter what the pressure and temperature are, so long as they stay constant. Then your stoichiometry just turns into mole ratios, but you don't have to first convert things to moles, which is very, very different. We've always had to do that in the past, and we couldn't compare masses of something and volumes of something else in solution or a solid, because in the solid and liquid phases, matter is very, very tightly packed together. So because in gases, what we're really doing is essentially converting the empty space. The empty space is identical in a gas. So again, what I mean by this is if we have a sample of hydrogen, there's such a giant spacing between particles that you have mostly empty space. And if we had a sample of O2, you really couldn't distinguish it, okay, because they have such gigantic volumes of empty space. We can essentially treat every single gas as identical. And because we can do that, and because our pressure and temperature, we can simplify a lot of the things we do in gases to just looking at volume relationships instead of having to do that extra step of converting things to moles, which does make it kind of nice. One last thing we can do with Avogadro's law is you can directly compare 2 samples. So for example, I had a container of, I don't know, we'll stick with it, with H2. Okay, and it's still at our same temperature and pressure, so our still pressure of 1 atmosphere, and the temperature still at 298 Kelvin. Okay, so let's say I have a sample of H2. It is 1 liter, and it has 1 liter, we'll say. We have another sample of gas here, and this one is O2. Okay, so same pressure and temperature, and this one is 1/2 of a liter. Okay, so what Avogadro's law allows us to do also is to say, oh my gosh, okay, so this has double the volume that this does. So therefore, I can say that that sample of H2 has 2 times the number of moles of gas as the sample of O2 does. So we're able to compare our samples based off of their volumes. So if, for example, I knew that this had, say, 1 mole, so this 1 liter had 1 mole, then I could say, okay, then that O2 has to have half a mole, because again, they're at the same temperature and pressure. We treat them identical, so we can use their volumes to compare the number of gas particles we have. So Avogadro's law is really kind of a nice thing. We're going to use it a lot in terms of all of the, laws named for people. Avogadro's we're probably going to use the most. Okay, so to kind of finish up our introduction here, we're going to look at some gas laws where we have a lot of our parameters or variables kind of sandwiched together. So the first one is called combined gas law. So if I keep N constant, a lot of times when you're looking at changes in gases from one set of conditions to another, it's pretty easy to keep N constant. You just have to, tie your balloon off or something like that. But a lot of times pressure, volume, and temperature all change. So if we combine, for example, Lussac's law and Boyle's law, we can get, the combined gas law of P1 V1 over T1 equals P2 V2 over T2. So again, 2 conditions set. You would put your first set of conditions in here and solve for whichever one you're missing. Okay, so for one condition, we are going to turn these proportion signs into actual equals. So for example, I can say volume is proportional. Oops, excuse me. Okay, so if we're turning all of these proportional signs into equal signs, if I multiply the P over and I get PV, I can turn that proportional into an equal if I set it equal to a constant. So P times V equals some constant. Okay, so if T is proportional to V, I can divide T over, and I can get V over T equals some constant. Same thing for volume and number of moles, divide that over, set it equal to a constant. Pressure and temperature, same thing. Okay, so if I take all of these relationships and put them together, and instead of having 1, 2, 3, 4 different constants, I roll that all together into one, I can get V times P over N times T is equal to some constant. Okay, so we call that constant. For gases, we call that R. R is the gas constant, and if I rearrange this, you'll probably recognize this into a different form of PV equals nRT. So keeping my PV over here and taking this NT and bringing it over here with my gas constant R, PV equals nRT. So experimentally, R is determined to be 0.08206 liter. Okay, so liter is our preferred unit for volume for gases. Atmospheres, our preferred pressure unit, mole, and then, of course, Kelvin, 0.08206 liter atmosphere per mole Kelvin. So you're going to experimentally determine this in lab. So that's a fun experiment. We also have a version of R where instead of having liter atmosphere, which is work, remember when in chapter 5 we talked about units of work being liter atmospheres. So we can convert that to joules using our relationship between liter atmosphere and joules and get 8.314 joules per mole Kelvin. So we're predominantly going to use this version. We will see this a little bit when we're talking about energy because this has our nice joule energy unit already built in. Okay, so ideal gas law. This works for pretty much any gas, but some gases are what we call more ideal than others. So good ideal gases do not interact. So an ideal gas or a gas is more ideal if they don't interact. So our noble gases are pretty great ideal gases because they're so inert, they don't really interact with one another. Also, particles are very, very small. So the smaller the gas is, the more ideal it would be. So something like carbon dioxide would be a terrible ideal gas because it's so large. Okay, so these equations that we talked about work for all gases, but they do work much better under ideal conditions, aka non-interacting and very, very small. So we can change the ideal gas law to be what we call the non-ideal gas law. So what that means is we put in a fudge factor for particles that strongly interact, and we can put in a fudge factor for particles that are pretty large. Okay, so A is our attraction factor. So that's going to change how we calculate pressure. So we'll have pressure, but also now with our attraction factor, it's going to be multiplied by n squared. So the more moles of gas you have, the more significant the attraction is going to be, and then divided by volume squared. So if they're tightly packed together, they're going to interact a lot more. But if they have a lot more sort of diffuse space, then they're not going to interact quite so much. So we have our attraction factor, which again, dependent on the gas, that's sort of assigned to each gas. So if you look up CO2, you could look up the A factor for CO2. So when we use the ideal gas law, we just put that in here. So if this attraction factor is 0 or very close to it, this whole thing drops out, and then you just get regular P. Okay, so we also have one for size. So that's our B factor. So that's going to change our volume. So again, remember for gases, our volume is really just that empty space. Remember when I drew this guy for us, I said we were really just comparing the empty space. This one has double the amount of empty space, so it has double the amount of particles. And so same thing here. So if these gases these particles get too large, you're not dealing with a whole lot of empty space anymore. Now you have to account for the size of particles. So again, this is something you would look up. So again, for my example of CO2, you could look this up, and then that's going to change how you calculate your volume. But again, as this factor becomes closer and closer to 0, like as again, if your your gas particle is getting closer, say to like helium size, then this is going to disappear and you get PV equals nRT. Okay, so these fudge factors do account for strong interactions and also particle size. Okay, so this concludes this portion of sort of our introduction into gas laws. For our in our live meets in session, we're going to use these formulas, Boyle's law, Charles' law, to actually practice calculating some different scenarios for gases.